In this video, we are going to take a look at the variation of the trigonometric functions. What that means, we are going to look at what happens as our angle theta does something, maybe increases or decreases, etc., something of that nature. What happens to the ratio that we get out of it? Do those ratios increase, decrease? Is there an asymptote? And these are the questions that we're going to answer. So what's the interaction between the input of the function, the angle, and the output of the function, the ratio? And this is really helpful for a couple of things. Let me write this down here. Really helpful for deriving the graphs of sine, cosine, and tangent. And it does make it helpful for remembering the trig values of our quote-unquote special angles. So those two things makes it very, very helpful. What I'm saying for that number 2 is this set of values for sine and cosine. You know that sine of 0 is 0, sine of pi over 6 is 1/2. That sine of pi over 4 is root 2 over 2, etc. And when you look at these values, you've got a lot of repeated values. It can be hard to keep them straight. You know that root 3 over 2 is the output of sine of pi over 3 radians, but it's also the output for cosine of pi over 6 radians. And it can be tough to get those, to keep those straight sometime. And being able to think about the variation of the functions can help. So that's what we're going to take a look at here. Let's just do these trig functions one at a time. We will start with the function sine of theta. And we're going to use the circular definitions here. So sine of theta equals y over r, where y is the y-coordinate of a point on the terminal ray of the angle, and r is the distance from that point to the origin. So what I want to think about is having some terminal ray. Now I'm going to have my initial ray. That's always where my initial ray is. And I'm going to think about having my terminal ray rotate through the first quadrant. Let's say it starts there, then goes there, then goes there, and all the way through. So what I would say here in a variation sense is as theta goes from 0 to pi over 2. Because all I'm thinking about is what's happening as I go from 0 radians, nice and down here, and having that theta get bigger and bigger and bigger until my terminal ray goes to that first quadrant. Well, what happens in there? Well, if I think about my circular definition and what's going on with my y and my r, if I choose some point on the first terminal ray for a very small angle, it's going to have some coordinates x and y. I don't really care about the x-coordinate because I'm dealing with the sine function. But that y-coordinate is going to be pretty small because the vertical distance between the point and the x-axis is pretty small. If I choose successive points along the terminal ray, and I choose those points in such a way that the radius, the distance from the origin to that point, stays the same. So all those r's are equal to each other. And I have these points, and I have now here a y sub 2, an x comma y sub 3, an x comma y sub 4, etc., etc. In this circular definition, the value of r is staying fixed, but the value of y is increasing. As my theta gets larger from 0 radians to pi over 2 radians, from 0 degrees to 90 degrees, these y coordinates, and I'll highlight them, these y coordinates get bigger and bigger and bigger. So as theta goes from 0 to pi over 2, I can say that sine of theta increases. I did not write that very well. Let's try that again. Sine of theta increases. It gets bigger and bigger and bigger. And that can be pretty helpful for remembering our sine function values. If I look at just this row right here, I can look at that as my thetas get larger right across here. It's alpha in this chart, but as I go across from left to right, I have increasing thetas. I have increasing inputs, 0, pi over 6, pi over 4, pi over 3, pi over 2. I also have increasing outputs, that my output goes from 0 to 1/2 to root 2 over 2 to root 3 over 2 to 1. So I have these increasing values there. So using that idea, that for the sine function, as theta gets larger, sine of theta gets larger, because the sine function is based on a y coordinate. This y coordinate right here. Get rid of that. This y coordinate right here. As my theta gets larger, this y coordinate gets larger, so the output gets larger. My answer to that function gets larger as well. So that can be a pretty helpful thing to help you remember here. The other thing, I've seen this written before, is you can use denominators of 2 and say that it went from 0 over 2, which is 0, to root 1 over 2, which is still 1/2. Keep the root 2 over 2, keep the root 3 over 2. And you could even make this 1 into a root 4 over 2, because root 4 over 2 is still equal to 1. So using that idea of variation can help us figure out that as theta gets larger, sine of theta gets larger, and it can help us remember those common values there. Similarly, if I work to my other quadrant, I'm going to erase all this. I'm going to leave my r fixed, you want to say there. But I'm going to erase this, this, and we're going to erase this because we don't have to fill it in. If I have some terminal rays now in the second quadrant, working my way around, theta is still getting larger. So theta is still increasing, but it's increasing from pi over 2 to pi. But as I'm doing that, and I take these points, successive points along the terminal ray, the y coordinates of these points are getting smaller and smaller and smaller. And since the sine function, maybe I should slide this out of the way and over to here. Since the sine function is really determined by the y coordinate, because we wanted to leave the radius fixed there. What happened to my little sign? The y coordinates are getting smaller. So as theta goes from pi over 2 to pi radians, the y coordinates on my fixed points are getting smaller. So the output of sine of theta, this whole value, is decreasing. And you can use similar arguments for quadrants 3 and quadrants 4 as well. So this is a variation of the sine function. I'm going to make another video for cosine with very similar explanations.